In this lesson, we're going to talk about permutations. So what is a permutation? Given a set of elements a1, a2 to an, a permutation is just an arrangement of that set. So for example, if we're given the set ABC, there are 6 permutations of ABC in a line. We could write them ABC, ACB, BAC, BCA, CAB, or CBA. So they're just a particular way to order the elements of the set. Now, in combinatorics, what we're interested in is the number of arrangements. So, given a set of n elements, how many permutations are there? So, for 3 elements, A, B, C, we have 6 permutations. The claim is that if a set A has n elements, then there are n factorial permutations. So, let's let x1, x2 to xn represent a permutation of the n elements of a set A. We can create a particular permutation by first assigning one element of A to x1, so it's got to have some value assigned to it, and then assign a second element to x2, which of course can't be the same element we assigned to x1 because we've already used that element. Then take another element and assign that to x3, and so on and so on. So we're looking at this as a set of experiments, and there's a total of n experiments. The first experiment is assign a value to x1. The next experiment is assign a value that isn't assigned to x1 to x2. And the next experiment is to assign a value that hasn't been assigned to x1 or x2 to x3. And all the way down to the end, so you just keep going, ... until you assign a value not assigned to any of the other values to the very last value. In other words, you just take the very last value you haven't used and assign that to xn. Now we can count the number of outcomes for each of these experiments. For the first experiment, we have n values because there are n values in A, and we can take any of them and make that the first element in our permutation. So for x1, there are n possible outcomes. Then, no matter which element we picked to make x1, there are n minus 1 left. Right? So we've used up 1 for x1, and now we're left with n minus 1 numbers left, and we can assign any of those to x2. And so there are n minus 1 possible outcomes for the second experiment. And once we've used that element up, there's only n minus 2 elements left. So once x1 and x2 have been assigned, there are n minus 2 elements left to assign to x3. And so the third experiment has n minus 2 possible outcomes. And we continue doing this until we get to the last experiment, which only has one possible outcome, right? Because eventually we only have one element left, and so that's the one we assign to xn. Now, the numbers in each experiment don't change based on the outcomes or based on the choices we've made in the previous experiments. So we can use the multiplication rule. And if we multiply the outcomes in all the experiments, well, we had n in the first experiment, and then n minus 1 in the second, and n minus 2 in the third, and so on, it's going to go down by ones all the way till we get to 1. So n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 times 1 in the end. And that is, by definition, n factorial. So I've included an example here that kind of goes through the steps in this proof. Let me just move my screen out of the way. So we could look back at our set A equals ABC. The first experiment is to assign some value to x1, and there are 3 possible choices, right? We could choose A or B or C. So in this example, we're just going to choose B. So let's say x1 equals B. And in the next experiment, we have to assign something to x2. But B is already taken, because B was taken as the first element. So x2 could either be A or C, and in this experiment, we'll just choose C. That leaves us with x3, our last element to assign, and we've already picked B and C, so the only possible outcome is A, and therefore x3 equals A, and this would give us the permutation BCA. So there were always 3 outcomes for x1, and no matter what I chose for x1, whether it's A, B, or C, I have 2 outcomes for x2. And then no matter what I chose for x1 and x2, I've always only got one choice for x1. One choice for x3. This is a typo. So then by the multiplication rule, the total number of outcomes is 3 times 2 times 1, which is 3 factorial, or is also 6 if you just compute it. We should point out that these numbers grow very fast. So there are 3 factorial, or 6 permutations of a set with 3 elements. For 4 elements, there's 24 permutations. And then if we go to 5, there's already 120, and then for 6, there's 720. So going from 3 elements, we have 6 permutations, to 6 elements, we now have 720 permutations. As you can see, this is growing really fast. And in fact, it's important to note this because when working with computers, if your problem is growing factorially fast, usually you can't even solve the problem that you're working on with a computer because it's so fast, the numbers get so big that the computers can't handle it for very large numbers. So now that we've seen what to do, whenever we have n distinct elements, how do we count whenever we have repeated elements? So, for example, let's look at the number of ways we can permute the letters of the word ball. So these are permutations, but we don't have 24 permutations because there are 2 L's. And for example, if we have, well, the word ball itself, the first L or the second L are identical, so it doesn't matter which order they come in. And so therefore we end up with these 12 permutations instead of 24. And if you have some identical elements, what you can do is kind of group these elements into their identical types. So let's say that we have n elements, some of which are identical. So if there are n1 elements of type A1 and n2 elements of type A2 and so on, then up to nk elements of type AK, so there are k types, the number of permutations is n factorial divided by n1 factorial times n2 factorial down to nk factorial. So if they're all distinct, as we were looking at above, each type would be in a class of its own, so each one would be 1. And in fact, we would get n factorial divided by 1 factorial, 1 factorial, 1 factorial, all the way down to 1 factorial. And this would be n1 factorials, which would equal just n factorial. This is the case if each element is distinct, so there's n factorial permutations. But whenever the sum of them are the same, we have to cancel off things. So let's look at this up here first, at the word ball, just so we can see what's going on. We have 4 total letters, so there's 4 factorial, things that we're permuting. There's 1 B, so we have a 1 factorial. There's 1 A, so we have a 1 factorial. But there's 2 L's, so we end up with 2 factorial, which equals 24 over 2, which equals 12. So that's the way to actually compute with this. And this is the formula. We can go through the proof. The proof is basically using the same idea as above, except for now we have to cancel off all the repetition. So I think it's better maybe just to look at the example of the proof, and instead of just me trying to talk through the proof itself. So let's say that we're looking at the permutations of the letters A, A, B, B, B. There are 2 A elements, well, we could say 2 type A's and 3 type B's, because those are identical. And what we're going to do is number these so that they can be distinguished. So we'll call them A1 and A2, and B1, B2, and B3. That way we can tell like which A is which, right? So if I permute them as to B1, B3, A2, B2, A1, I can distinguish that from like B1, B3, A1, B2, A2. So if I swap the A1 and the A2, I can tell which order they're in. But whenever I can't distinguish between them, all of these are going to look the same, right? So there are 6 ways to permute the B's. For example, I could take B1, B3, B2, or B1, B2, B3, or B3, B1, B2, and so on. And so whenever I count the number of permutations, if I can distinguish them, I have 5 factorial ways to permute these numbers, or these letters, right? So 5 factorial ways to permute A1, A2, and B1, B2, B3. But I'm going to get 6 permutations for every place that A1 and A2 go that are going to be identical, because they're all going to just look like B, B, A, A, B, A. And so that's the permutations of the B's. That's why I need to cancel that. So I had 5 factorial, but I need to cancel this 3 factorial because of every way I can permute the 3 B's. And similarly, for each way that the B's go, B1, B3, B2, with a gap there, we could have A1 and A2, or we could permute the A's to be B1, B3, B2, and then this could be A2 and A1. So for each order of the B's, I'm going to get 2 times the number of permutations because there are 2 factorial ways to permute the A's. So I need to also divide by the 2 factorial so that I can cancel out these 2 times repetition. And this would be a 6 times repetition, right? Because there are 3 factorial or 6 ways to permute the B's. And that's why you divide by the 2 factorial and the 3 factorial. Which means that the total number of ways to permute AA, B, B, B is 5 factorial divided by 2 factorial times 3 factorial, or 10. So if you go through the example problem, hopefully you've done that, or don't look at the solution before you try it for yourself. But if you have 3 red balls, 4 blue balls, and 6 yellow balls, how many ways can you put them in order? Well, there are 13 total balls. 3 plus 4 plus 6 is 13. And there are 3 classes, red, blue, and yellow, with 3, 4, and 6 elements. So we have 13 factorial ways to order 13 balls, but we have to cancel 3 factorial for the 3 ways we could arrange the 3 factorial ways we could arrange the 3 red balls, 4 factorial for the 4 factorial ways we could arrange 4 blue balls, and 6 factorial for the 6 factorial ways we can arrange the 6 yellow balls. And this gets us 60,060. So there are 60,060 ways to arrange 3 red balls, 4 blue balls, and 6 yellow balls. Pretty big. It might be bigger than what you expected. I guess if any of you live near the fast food chain Sonic, you'll see that they advertise they have millions of drink options, and you can compute that with these permutations. So maybe you can figure out how many drink options there are whenever you add syrups to drinks. And in fact, Starbucks, which I guess is everywhere, if you look at the different syrups that you can combine, you can figure out how many different drinks options you can make at a Starbucks, and it's probably a lot higher than what you expect.